Simone Gutt. Our first speaker is Simone Gutt, who's joining us in Brussels, and she will tell us about minimally and maximally non-integrable, almost complex structures.
Thank you very much. I first would like to thank the organizers for inviting me, and I regret not to be in presence in Freiburg. What I shall talk about today is work on how to choose almost complex structures on a manifold. So we started this a few years ago with Michel Kähler, and we have pursued that with two students, PhD students, Maxime Gérard and Manar Ayani, and recent discussions with Jean Gutt. We have seen last week that when you deal with quantization, a symplectic manifold is usually not enough. You need some extra data, like a connection for deformation quantization or a polarization for geometric quantization. And often these can be related to the choice of a complex structure, or more generally, an almost complex structure. And that was the motivation in studying those classes. So the plan of my talk is the following. I shall first recall what are complex, almost complex structures, and what are the distribution one can associate to an almost complex structures. And then I shall speak of this notion of maximally non-integrable almost complex structures, giving examples on twistor spaces and on some four symmetric spaces. And then I shall suggest the definition of minimally non-integrable almost complex structures, which is related to the largest possible transverse complex structure. So let's first recall elementary things, that here I shall always consider smooth manifolds, which are topological space locally modeled on open subsets of Rn with smooth coordinate changes. And one says that there is a complex structure if the manifold is complex, which means that you can see this topological space as locally modeled on open subset of Cm, but with holomorphic coordinate changes. And an almost complex structure on a smooth manifold is a smooth section of the endomorphism of the tangent bundle, which squares to -1. So whenever you have that, you have a splitting of the complexified tangent bundle into +i and -i eigenspaces for J. And when you start with a complex structure, you have an almost complex structure which is associated to it. When you choose any local holomorphic coordinates, the almost complex structure maps d over dxj, so the tangent vector to the real part of the jth coordinate to the tangent vector to the imaginary part of this coordinate dyj, and of course maps dyj over minus dxj. So for instance, in the case of the sphere, it is just in each tangent plate the rotation of 90 degrees. And we say that an almost complex structure is integrable if it comes from a complex structures on M. And to any almost complex structure, one associates its Nijenhuis tensor or Nijenhuis tensor torsion, which is a map which associates to two vector fields X and Y on M, a new vector field, which is given by the bracket of jx, jy minus the image under J of the bracket of jx and y minus jxjy minus xy. And you have the well-known Newlander Nirenberg theorem, which states that an almost complex structure is integrable if and only if its Nijenhuis tensor vanishes. And saying that the Nijenhuis tensor vanishes is the same as saying that the bracket of two sections in the plus I eigenvalues of J is again a section of this T10 bundle, as can easily be seen. You want the bracket of two vector fields of the form X minus JX, Y minus JY of the form Z minus IJZ. And this says that the real part of the bracket must be equal to J times the imaginary part of the bracket, which is minus GX Y minus X GY. So you immediately get that the NJ is equal to 0. Now, if when look at the case where the manifold is symplectic, so the manifold has a symplectic structure, a non-degenerate closed-to form, then an almost complex structure is said to be compatible if at each point it is in the symplectic group. So if omega jx jy is equal to omega of xy, and this can be equivalently obtained by asking that if you define gj of xy to be omega of xjy, this is a symmetric tensor. And we say that the almost complex structure is compatible and positive if furthermore this metric is positive definite. And you have the well-known theorem that on any symplectic manifold there exist positive compatible almost complex structures, and the set of those is path connected. And in fact, how do you show that? You take any metric, any Riemannian metric, you express the metric in terms of omega and a field of endomorphism A. If you look at the adjoint of A with respect to this metric G, you have that it is equal to minus A because of the skew symmetry of omega, and you set J to be the inverse of the square root of A times its adjoints times A. So you just look at the polar decomposition of A, and you can readily check that this is indeed an almost complex structure. And of course, the fact that there exist a lot of almost complex structures has been used in the study of some homology related to pseudo-holomorphic maps. And this was at the root of symplectic topology in all the work of Gromov. But here we would like, on the opposite, to say when there are some special J's. Can you pick J's which have particular properties? So let's recall that what one calls a Kähler manifold means that you have a symplectic manifold with a compatible positive almost complex structure J, which is integrable. So you have a complex structure. And examples are the sphere, the projective space, any one-dimensional complex manifold, and so on. Now, usually, Kähler manifold arise in the framework of Riemannian geometry. So if you start with a Riemannian metric G and an almost complex structure J, which is compatible in sense that it's an isometry at its point, then if you set omega of xy, which is G of jxy, it's automatically skew symmetric. So it gives the two form. And if you look at the Levi-Civita connection associated to your metric, you always have a relation between the covariant derivative of J with respect to the Levi-Civita metric, the differential of omega, and the Nijenhuis tensor of J. So this automatically tells you that if you start with a Riemannian manifold, and if you have a compatible J, it is scalar if and only if the covariant derivative of J with respect to the Levi-Civita connection is 0. Indeed, for the Levi-Civita connection, the covariant derivative of G is 0. Now, if the covariant derivative of J is also 0, the covariant derivative of omega is 0. So the differential of omega is equal to 0. And from the above equation, Nj is equal to 0. So indeed, you have a symplectic manifold with a compatible J, which is complex, and vice versa. Or you can also say that this is true if and only if J is complex, so J is integrable, and what is called the form is closed. Okay, all these are equivalent. And in the framework of Riemannian geometry, what they call an almost scalar manifold is a Riemannian manifold with a compatible almost complex structure such that d omega is equal to 0. So equivalently, it is just a symplectic manifold with a positive compatible almost complex structure J, but of course, which is not automatically integrable. And a first example of a symplectic manifold which does not admit any Kähler structure has been given by Thurston in '76, and it is an example of what is called a nil manifold. So a nil manifold is the quotient of a nilpotent Lie group. Here the Lie group is the direct product of the Heisenberg group in 3 dimensions and R by a lattice. And the lattice here is just Z to the 4. And you have Malsev criteria, which says that when you have a nilpotent Lie group, whenever you can write in the Lie algebra all the structure constant as rational numbers, then you always have a lattice, which means a subgroup such that the quotient is compact, a discrete subgroup such that the quotient is compact. And so on the group G, you look at the left invariant two form given by dx1 dy1 plus dx2 dy2. So it gives a symplectic structure on the quotient. Why is it not scalar? Because if it was scalar, then automatically the first Betti number of the manifold would be even, because the Betti number is the dimension of the RAM cohomology of M, which splits as using the del bar operator as H10 plus H01, which are in duality, so the dimension would always be even. And here, well, if you look at the dimension of the first cohomology group, well, the first cohomology group is the abelianization of pi1. Pi1 of your manifold is your lattice, is Z4. And if you look at its abelianization, well, you see that in the bracket, everything is in dimension 1. So the rank of this is 3, which is not an even number. So indeed, this cannot have any Kähler structure. So we were interested in looking at properties of the Nijenhuis tensor to see if one could, at least in the symplectic case, extract some particular J's by asking conditions on the Nijenhuis tensor. And a first way that is used in geometry to select some objects from a tensor is to look whether you can annihilate some components of the tensor. But to have a meaning, those components must not depend on bases. So you have to look at the decomposition of the tensor under the group which preserves the structure. So here, a symplectic structure and an almost complex structure. So looking at properties of the Nijenhuis tensor, of course, it's Q-symmetric in X and Y, it's antilinear in J, and when you are in the symplectic framework, you have that the cyclic sum of omega of Nj xyz is equal to 0. And what we showed with Maxime Gérard is that if you look at the space of tensors which have the same symmetries of this Nijenhuis tensor at a given point, if you look at the decomposition under the unitary group, so which is the set of linear transformation of your vector space, which preserves the symplectic structure at that point, and which commutes with the complex structure, this is isomorphic to the unitary group, then this space is irreducible. And this tells you that there is no way you can ask for the vanishing of some component. The only natural way is to ask for the vanishing of the whole tensor, but then you are back in the Kähler situation. So we wanted to have information from distribution associated to the Nijenhuis tensor, and we looked at the image distribution. So at any point, it's the span of the image of Nj at the point. It is stable under JP, so it's a symplectic distribution. It is smooth, but the dimension may be varying. And one can show that if the dimension of the manifold is 4, then the dimension of the image is automatically 0 or 2. But if the dimension is bigger than 4, then we have examples of symplectic manifolds, which are in fact nilpotent Lie groups with left invariant symplectic forms and with a left invariant J, where the dimension of this image, since it's left invariant, it's constant, but it can be any possible even number, even maximum, the whole dimension. And we have examples where this distribution is involutive or not, and you can even have that the omega orthogonal of the distribution is involutive or not. And this leads us to the first definition of what is a maximally non-integrable J. And we shall say that an almost complex structure on any manifold, not necessarily symplectic, is said to be maximally non-integrable if this distribution image is the whole tangent space. And we showed that if you assume that this image, if you are in the symplectic context, back to the symplectic context with a compatible J, and if you assume that the image distribution is parallel with respect to the Leibniz-Civita connection, so this says that if you take any vector field on the manifold and any section of your image distribution, then the covariant derivative is a section of the image distribution. So that means being parallel, then automatically M is locally a product, and this is global under a topological assumption on the manifold, and if the connection is complete, but always locally a product, on one hand on a Kähler manifold, and on the other hand of one of those manifold, almost Kähler manifolds, so triples M prime, omega prime, J prime, where this J prime is maximally non-integrable. So this really appears as building blocks. Of course, to have that the image is parallel, a sufficient condition would be just that the tensor Nj is itself parallel, but in fact, if the tensor Nj is parallel with respect to the Levi-Civita connection associated to the metric built from omega Nj, then the J is integrable, Nj vanishes. And examples are given by almost complex structures on twistor space. So this we studied with John Hornsley. If you start with a Riemannian manifold, which can be oriented or not, and which can be even pseudo-Riemannian or Riemannian, you look at the bundle of adapted frames, so pseudo-orthonormal oriented frames on your manifold. If it's Lorentzian, you also take time-oriented. You take the bundle of frames so that the group acting is connected, is a natural connected component of the group. And you look at, you define the twistor space to be the bundle on your manifold whose fiber is the bundle of compatible complex structure on each tension space. So what does it mean, compatible? So you have that a complex structure at the point P is compatible if you can find a frame in your principal bundle above your point P on the manifold. So psi P is a frame, so it's a bijection between R2N and the tangent space to M at P, such that if you look at psi P composed with JP, composed with psi P minus 1, it has a canonical form, which is 0, the identity n times m minus the identity 0, which we shall denote by J0. So if you look at this bundle, you see that twistor space, well, if you have given one frame, you have automatically one JP given by this expression. And if you act by the unitary group, you would have the same JP. So you can see the twistor space as the quotient of the principal bundle by the unitary group. When I say unitary, it's unitary or pseudo-unitary. It's the subgroup of your group acting on the principal bundle of transformation with commute with J0. And if you look at the Levi-Civita connection on your Riemannian manifold, it gives a horizontal space in the principal bundle, which are invariant by Rand translation. So it gives us a horizontal space on your twistor space, which means that the tangent space at each point of the twistor space splits in a horizontal and in a vertical part. And the vertical part means you just look at a given point at complex structure, which are tangents to JP. So if you take a curve from a JP to have another complex structure, well, you add an element in the pseudo-orthogonal group which anti-commutes with C. And then you can define two naturally almost complex structure on any twistor space. On the horizontal space is diffeomorphic to the tangent space to M. And on this space, you have that JP is a complex structure. So you do the actions of JP on the horizontal vector. On the vertical vector, you see that an element in the vertical vector is such as C. If you just multiply it by GP, you have another such vector. It is the canonical structure on the space of compatible complex structure on a vector space, on a vector space with a metric. So you have those two you have those two almost complex structures which are natural, and you have a theorem that J plus is integrable if and only if the vile component of the curvature vanishes, phi component part of the curvature. When I say the curvature, I mean the curvature of the Levi-Civita connection. Connection on MG vanishes. So this is true in the non-oriented case in all dimension, and in the oriented case, non-oriented or oriented, and the dimension bigger than 4. This was well known in the Riemannian case, and it was used by Atiyah to transform Yang-Mills equation on M to Cauchy-Riemann equation on the twistor space. And in dimension 4, in the orientable case, then it is integrable if and only if you know there that the vile component of the curvature splits into a self-dual and anti-self-dual part, and it depends on the signature. So if the self-dual part self-dual part vanishes of C, of the vile part vanishes if the signature is 2, 2, and it's if and only if the curvature if self-dual in signature 4, 0 or 0, 4. And this you find often in the literature with slight mistakes. So, and what we obtained is that if the curvature, if the space has constant sectional curvature, G minus, which is in all cases never integrable, is maximally non-integrable. The G minus was introduced first by Ilse and Salomon and was used in the study of harmonic maps from a Riemann surface into a Riemannian manifold. And so these are geometric natural examples of things which are maximally non-integrable. So let's look at examples. If you look at the sphere S2n with its standard metric, the bundle of oriented orthonormal frame is S2n plus 1. And so it's fibers on the sphere. And you can see that Z plus identifies with the orbit of an element in the Lie algebra of SO2n plus 1. So it is symplectic. You can check that the two natural almost complex structures. So if you identify the tangent bundle to the base point to the twistor space as a supplement in the Lie algebra of SO2n plus 1 of the Lie algebra of the element of SO2n which commutes with J naught, what you obtained are the elements of this form. So you have on one hand the U's which corresponds to the tangent space of SO2n, which is the horizontal space. And on the other hand, you have the elements in the Lie algebra of SO2n+1, which are supplementary to UN, so which anti-commute with G0. And you look at both the structure we just defined. So on the horizontal space, it's plus or minus G0. On the vertical space, it's a multiplication by G0. And you can see that G plus is compatible, positive, and integrable. So that was the one used by Atiyah. And G minus is still compatible. It's not positive, but it's maximally non-integrable. And in a similar way, you can look at hyperbolic spaces, which looks exactly the same, instead that you have SO1 to n instead of SO1 plus 2n. It is again the orbit of the same element which belongs to this new algebra. You identify the tangent space to a base point of this hyperbolic space to a supplement in the Lie algebra of SO1 to n to the Lie algebra, of UN. So you have on one hand the supplement to the Lie algebra SO2n+1. So these are again given by vectors in R2n and corresponds to the horizontal space at the base point. And a supplement of UN in SO2n, which are again the matrix which anti-commutes with G0, which is a vertical space. So G plus or minus is again G plus or minus on the horizontal space, so on the U, and the multiplication by G0 on the vertical space. And in this case, G plus is still, as we said, integrable and compatible, but it's not positive, whereas G minus now is compatible, positive, and maximally non-integrable. And in fact, those construction, the construction of the examples can be generalized further to the case of some four symmetric space. So what means a four symmetric space? Well, it's a space with symmetries. So symmetry means that you have a map from M to M. So the image you will denote as the image under the symmetry at X at the point Y, which has the property that X is an isolated fixed point. And this you ensure by asking that the differential of X at X has not one as eigenvalue. And you ask, as usual, the property of the symmetry that if you conjugate Sy by Sx, it's the symmetry with respect to Sxy. But this time, what you ask is that Xx to the fourth power is the identity. So it's usual symmetric space, you have that the square is equal to the identity. A k-symmetric space, you ask that the kth power is the identity, and the other assumptions are the same. And as in the symmetric space, you can define a group of transvection which is generated by the product of symmetry and the inverse of another symmetry. And you can see that this group acts transitively on the manifold. And so any four symmetric space can be viewed as a homogeneous space where you have a Lie group, where you have an automorphism, which this time is a fourth order automorphism of G. So this means that sigma to the 4 is the identity. And H is contained in the fixed point set by G tilde and contains the connected component, just as in the usual symmetric space business. And examples of those symmetric spaces are given by the two examples we saw before. So more generally, if you have that this element, if you have a group such that this element is in the Lie algebra, so you take a group such that the identity k fois k and or g naught in dimension 2n is in it, and such that 0, 0 to n is in the Lie algebra. And if it's a simple, or it can be the extension of a simple group by multiple of the identity, so essentially any classical simple group is okay, then you can look at the automorphism, which is the conjugation by this element, which is clearly of order 4. It is the orbit of S tilde in G. So if G is simple, it has a symplectic structure. And if you look at the group of stable points, it factors over the symmetric space, which is the quotient by the elements of G, which are fixed by the square of this automorphism, which of course is an the square of sigma tilde is an automorphism which squares to 1. So this is a classical symmetric spaces. And you can again look at the decomposition of the decomposition at a base point of the tangent space. It will again be of this form, except that now you have something on left-hand side, which is K, but which is in the stabilizers. And those are now matrix, not just line. You do an equivalent G plus or minus, and you have again, in all those cases, that G plus is integrable. It is compatible with the complex structure coming from the orbit, but it's not in general positive. And G minus is maximally non-integrable. Those examples appear in the thesis of Manard-Hayen. So you have lots of nice geometrical examples of maximally non-integrable J's. Now, what does it mean to be non-integrable? We said that whenever we have an almost complex structure, you can decompose the complexified tangent space into plus and minus eigenspaces for J. And of course, you have bijection between the space of vector field and sections in 1, 0, which maps a vector field X for 1/2 X minus ijX, and similarly for a map on 0, 1 vector, which means that any section of the complexified tangent space splits in this way as an element in 1, 0 and an element in 0, 1. Now, given any smooth, real or complex distribution D, and whenever I have a distribution, I shall write in boldface the distribution and curly the sections of distribution, one defines the derived flag of the manifold as the sequence of distribution. The first one is D, the second one is D plus the brackets of 2 elements in D, and so on. So, of course, if at any point one of those distributions is involutive, then all the next ones remains the same. So it's a way to build from a D to increase it to try to get an involutive distribution. So if you start with the distribution 1, 0, then if you look at the derived distribution, well, you have to look at the bracket X minus XJX minus IJY. And so if you look at this expression, it's A plus of something, but that is already in T10J plus A minus of the real part minus J times the imaginary part And you see that this is exactly minus nj of xy. So indeed, the first derived distribution is given by section of T10 plus sections of the image of Ng or section of its complexification. It yields the same results. And then we were interested in the next level. So of course, we come back to the first thing, that T10 is involutive if and only if the Nijenhuis tensor vanishes. But what about the next level? What is the condition for this derived distribution to be involutive? And one checks that the first derived distribution of T10, so this new distribution, which is the sum of T10 and the image of Nj, is involutive if and only if you have this condition. To find that it is a necessary condition is easy. You take the bracket of an element in T10 and an element in the section of N. So of course, this is A plus of something plus A minus, you remember, of Xn plus J, it was minus J times the imaginary part. And so you have that this must be in A minus of Nj. So you have, it is a necessary condition, and one can show that it's a sufficient condition. There is, of course, an extra condition saying that if you have this condition, then Im of Ng is involutive. But this you can check. This really depends on the definition of the image of Ng. So we have a necessary and sufficient condition for the first derived distribution to be involutive. And I shall show you that this condition is saying that you have the maximal possible transverse complex structure. So let's go back to some facts about transverse structure. So whenever you have a smooth, regular, involutive distribution on a manifold, you shall define transverse things which would correspond to the things that you would have on the space of leaves of this distribution if this space of leaves had a nice smooth manifold with the natural projection submersion. So for instance, what would correspond to the tangent bundle, to the leaf space? It is this notion of normal bundle. So the normal bundle is just obtained at each point by the quotient of the tangent bundle at that point by the image on D, and you have a natural projection from Tm onto Q. And clearly, if you have a leaf space, the pullback of the tangent bundle to the leaf space would be isomorphic to this normal bundle. What would be a tangent vector? Well, if you imagine a tangent vector on the leaf space, you can lift it back as a section of your pullback bundle, but which is constant along the leaves. So it is a section little u of your normal bundle Q, such that a sort of Lie derivative in the direction of the distribution is zero. And indeed, you have an action of section of your distribution on sections of the normal bundle, which are just given by the projection of the bracket where big U is a lift of little u. And so we defined a vector field on M to be foliated if whenever you take a section of your distribution, the bracket of Fx is still in D. And foliated vector fields will be designed by Xi dm, and a transverse vector field is just an element of the quotient of foliated vector field by D. Because of course, when you lift your little u, it is defined up to an element of D, and saying that it's invariant along the leaf, say that the lift is foliated. So what is now a transverse first almost complex structure? Well, a transverse almost complex structure would correspond to an almost constant structure on the space of leaf. So this is a section of the tangent bundle to which squares to -1. So it lifts to a section J tilde of the endomorphism of Q, which squares to -1. But again, it's constant along the leaf. So the leaf derivative of this J tilde with respect to a vertical vector field, so a vector field with values in the distribution is 0. And this writes explicitly as when you take any lift of J as saying that the bracket of a section of D with Ju minus J times the bracket of F and U has values in the distribution. You see that now we are very closely back to the relation we had, and we say that a transverse complex structure is of course a transverse almost complex structure, but which is integrable. But this means that the Nijenhuis tensor must have values in D. So this tells you that the projection of the equivalence of the Nijenhuis tensor that you build from any lift of J tilde must project on your manifold. And you can observe that this relation is indeed well defined since you had the condition to have an almost complex structure, which I rewrote as 2. And so, having those general definition of transverse structure, I want to know when does an almost complex foliation has an almost complex structure induce an almost complex foliation with a transverse complex structure. So if I start again with an almost complex structure, and I look now at an involutive distribution, which is stable under J, then we have just seen that one has a transverse complex structure if and only if the bracket of GU with any section of D minus GUF is a section of D. And you have a complex transverse structure if furthermore your distribution contains the image of NJ. So what does it mean? From the computation we just made, it means that an almost complex structure will induce a complex transverse structure if and only if you take an involutive distribution stable under J such that the D plus T10 is involutive. So this tells you that when you have given an almost complex structure on your manifold, the biggest transverse structures that you can have, whatever you have, is certainly of dimension at most the dimension of Nj, because if it's involutive, it must contain Nj. And so the best you can do with an almost complex structure, the biggest complex part that you can have, so the biggest complex transverse structure, is obtained if the image of Nj itself is an involutive distribution. So this is equivalent to say that the dimension of the image is constant, and you have the condition we had obtained, so that T10 plus N, which was the first derivative of T10, was involutive. So if you have the relation that we obtained, which I think is a very nice relation, which is this one, and if the dimension is constant, then automatically the image is a distribution, involutive, so you have a foliation the leaves inherit the almost complex structures that you have, and you have the transverse complex structures. And so we suggest to define an almost complex structures to be minimally non-integrable if the dimension is constant, and if possible, the smallest possible dimension, which is not 0, of course, which is 2, and if you have this condition that the Lie derivative of J in the direction of a vector field in the image of Nj maps T to M to sections of the image of Nj. Okay, maps a vector field into that. And one example, let me come back to the classes that we had last week. For quantization, we were looking, when we're dealing with complex polarization, to a Kähler manifold, and we were looking at line bundle over the Kähler manifold. And it was said that different complex line bundle were parameterized by H, M, with values in Z. And for on this, you can put a Hermitian structure and you can put a connection. And for quantization, you were asking that the curvature of gamma was proportional to omega. So in particular, because you have a Kähler manifold, it was of type 1,1. And then you had a holomorphic structure on L, which was defined, which means that you have a J on the whole of L, which is integrable. But in general, you cannot have that for any line bundle. You can do that, so you have a holomorphic structure, which of course is equivalent to a complex structure on L, such that the projection is holomorphic, if and only if the first Chern class of your line bundle can be represented by a 1,1 form. And this is, of course, always true if the manifold is a complex dimension of complex dimension 1. But in more general cases, you can have elements in H2 of MZ, which cannot be represented by a 1,1 form. And in all those situations, the natural, almost complex structure that you build in this way is, in fact, minimally non-integrable. You would have that the image distribution is the vertical distribution. And so those are examples which shows that it's, I hope, an interesting notion. And so we can do that on group, but in view of the time, I think I shall stop here. So those equations can be readily be written for Lie groups. If you take a Lie group and if you want a left invariant almost structure, everything is defined by the value at the identity. So you have an algebraic Nijenhuis tensor on the Lie algebra. The image of Ng is left invariant, so of constant dimension, and to have our proposition, it is exactly the same type of equations that you have algebraically in the Lie algebra, so that you know that the image defines a foliation, that the leaves carry an induced almost complex structure, and that the almost complex structure induces a transverse complex structure. And I want just to point out that this condition is between being a subalgebra, which would just say that image of Nj is involutive, and being an ideal, which would of course say that you have a group structure on the quotient. And examples of an example of that is given by what I started with, which is Thurston's example of a manifold which does not admit a Kähler structure. It is one of those examples where you have a minimal, almost minimally non-integrable, almost complex structures. And I shall skip the fact that it writes also nicely for homogeneous spaces, and I end up with giving a few references. So those are the two theses I spoke about. There is a paper on twistor spaces and a paper which is under press in Journal of Symplectic Geometry, which starts with all the things associated to symplectic manifold. The last part, which is on minimally non-integrable, almost complex structure, is work going on with Jean, and there is not yet anything written. Thank you for your attention.
Thank you so much.
I have a problem that I don't know how to stop the sharing of my screen. Probably Zoom. I shall, okay.
So are there questions, please?
If there are questions, I don't hear anything.
Hi, Simone. You can see me? Oh.
No.
Hello, Simone?
Yes, I hear very, very faintly. I don't know why it's so faint. Wait, maybe now I shall hear better.
Okay, you can hear me?
Yes, very well. Thank you.
Great. This is Pierre. I don't know if you see me.
I don't see you, but I hear you and I recognize your voice. So
at the moment I am waving.
you are moving, so probably you don't have an image or something.
Yes. Thank you for this great talk. I have too many questions, but maybe I'll try to start with 2 or 3 questions.
Okay.
The first question is, okay, you have showed this this space of the tensors that 2-1 tensors T that you defined, right? The ones that have the same properties as the J's, right?
Yes.
And you said that, okay, you have a irreducible representation of the unitary group, right?
Yes.
So my question was, okay, is there, so it means that in particular you have a bundle of these guys, right, over your symplectic manifold, which is canonical, right? And I was wondering if there are some interesting differential operators on the sections of this bundle, a little bit in the spirit of Dirac operators in the case of Riemannian manifolds, spin manifolds.
So any sections of a Nijenhuis tensor would be in that bundle. Right. There is something I didn't speak about today, is that there is so it is very much linked to, of course, any almost complex structure. From any section in the bundle of almost complex structure, you have a section in this special bundle with those symmetries. And you have a Dolbeault operator even for almost complex structures. So that is something that I would like to study now in this minimally non-integrable setting. You know that the usual Dolbeault cohomology, I should have stopped my things, but it was so difficult already to log in the first time that I don't dare. Usually you have this decomposition into T10 plus T01, So for forms, you have one forms, you have also a decomposition into omega 10 or omega 01, which vanish, respectively vanish on T01 or T10. So for P forms, you have a decomposition in omega K plus K prime with K plus K prime equal to P. And when you have a complex structure, what you have is that the differential of a PQ form is included in the P plus 1Q or in the PQ plus 1 forms. And this gives you the del bar and the del, respectively, the del and the del bar operator. But if your J is not integrable, then it decomposes into 5 pieces, because if you compute a PQ form on P minus 1 vector field in T10, but Q plus 2 vector field in 01, when you take the bracket of those two vectors, you have a component in the 10 part. And this is exactly given by the Nijenhuis tensor. So this Nijenhuis tensor goes into the definition of the operator, which is often called mu, which is the projection of the differentiation from PQ form to P minus 1 Q plus 2 forms. And this is the lowest you can get. So this mu squares to 0. So you can look in the space of forms at the homology of this mu. Of course, in the case that J is integrable, you get all the PQ forms, but if not, you take PQ forms which have a property relative to this tensor and J, and maybe one can extend it to those tensors T that you are speaking about. And then on this space, if you look at the projection of differentiation from PQ to, so I spoke of mu, which was on P minus 1 Q plus 2, and you have the next one, which is called del bar, which is mapped on P Q plus 1. But if you look at twice this thing, so this is the usual del bar operator, which still exists in the almost complex structure. But what you see is that if you do the mu I defined before, mu del bar plus del bar mu, it is 0. So you can compute the del bar cohomology on these cohomology spaces. And so maybe you can do the same type of operators with any section of the bundle you were speaking about, but I haven't tried. Okay.
Okay. Thank you. May I ask another question?
Yes, sure.
Yeah, so I have seen you have showed motivations for studying these structures in geometric quantization at the end of your talk.
Yeah.
I was wondering, what about the motivation in foliation theory? So the question is, how bad could be a J-stable involutive distribution? Because do you have something like ergodicity somewhere? I mean, is there something really what is the space if you have a J involutive distribution on your manifold? What is the space of leaves of this thing? As soon as you are requiring J invariance, so what can you say? Is the space of leaves, could it be very bad, like non-separated, for example?
As you know, I don't know much about foliation. I'm learning quite a bit for this. And I don't know, it's very particular because of course the dimension is of all the leaves are even because they are stable by J. So it's not just one-dimensional singularities, but I don't know how bad the singularities can be. Of course, when I am in homogeneous situation, the dimension is at least constant. Yeah.
Yeah, that would be great. I mean, to have, I think, I'm not sure, but I think that would be great to have bad situations.
Sure, that's why I tend to start with those minimally non-integrable, but which could be, of course, in the definition. It could perfectly be singular to see what can happen when you have those two-dimensional leaves.
Right.
At most two-dimensional leaves.
Right. Right. May I ask another question, or it's over? Oh, thank you very much. The answer is only half an hour.
Okay.
So I was thinking about families of your
J's.
J's. No, families of these manifolds. So I was thinking about, is there some Poisson thing that you could, you have a Poisson manifold, and of course you have the leaves, right?
Mm-hmm.
Leaves, and you can start looking at what you have done on each symplectic leaves, and then you can glue everything because you have a Poisson structure. I mean, you can look at the families of these symplectic leaves, which is precisely the Poisson manifold, right?
Mm-hmm.
I was wondering, is there something you can do at this level? For example, having a singular Poisson structure. Does it glue somehow? If you have a Poisson manifold, and if you do what you do on every leaf, does it glue nicely? Do you have some kind of Poisson version?
Well, here it glues by the NJ, of course, but that's a bit too big, as you say. It's the image of NJ.
Yeah. Because this would be an access to Poisson geometry if you have.
So you would have a sort of families of. You can see that those are families of two forms, or you can lift them back as a 3 tensor, whose totally symmetrized part is 0. So I don't know if things have been done with more than Poisson, but like 3 tensors.
Right. Okay.
You have that to glue, but I don't know how you can use it.
Right. Right. Okay. Thank you very much.
Are there any further questions for Simone? Doesn't seem to be the case, so let's thank her for her brilliant talk once again. And we'll have a very brief technical intermission until 11:15 before the next talk starts.